Great. And tonight's host is Bloomberg. So if you're interested in sharing your information, please click on the link in the chat and fill out the form. Welcome to building a scalable and highly available PubSub application with Women Who Code NYC chapter. I am tonight's moderator, Cindy Juarez. I am also a senior engineer at Bloomberg, and I am also a director with Women Who Code NYC since its inception in 2014. And tonight's speaker is Xiaoxiao Wang. She is a software engineer at Bloomberg for the PORT Analytics team. And I guess some logistics. So for tonight, I'm going to go over a little bit about what Women Who Code is. Then we'll have an intro from our hosts, and then the speaker will just take it away for the rest of the time, and we'll leave some minutes at the end for any questions you might have or any resources. Please remember to mute yourself if you're not talking, and turn on your video if you feel comfortable. So what is Women Who Code? It is a nonprofit global organization inspiring women in technical careers. It is in 20 countries and over 60 cities and expanding. Our mission is to inspire women to excel in careers, and our vision is a world where women are technical leaders, VCs, entrepreneurs, changing the world. For our code of conduct tonight, everyone here is a representative of Women Who Code, and as such, we try to form an inclusive community so that will empower your peers. So I hope everybody takes that and tries to be respectful of each other and encourage everyone in whatever we do in life. Some of our future events. Coming up, we have a coffee code break on Thursday, and on Friday we have another talk about how to organize your data store on the UI. So it's Redux best practices applied to Apollo client. And if you are interested in getting involved with Women Who Code, you can join the community either through Twitter, RSVPing to our events on Meetup, joining our Slack, or if you're interested in contributing even more, you can apply to speak, you can host or sponsor an event, or you can volunteer by emailing us at the email below. And now I will hand it off to Katie.
Awesome, thanks, Cindy. Let me share my screen. Okay. Can I get a thumbs up if everyone can see this? Perfect. Okay, awesome. Well, it's so nice to meet everyone here. My name is Katie Golub, and I'm one of the tech recruiters at Bloomberg. I've been at the company about 6 years now, and I'm so excited to have you all here. I wish we were together in our offices, but welcome to my apartment, and it's great to have you all. So I'm going to give a little bit of background information about Bloomberg, who we are, what we do, some information about our core product and technology. And then also, as Cindy mentioned, there's a form that you can fill out if you'd like to be contacted about opportunities. Even if it's on an exploratory basis, we can set up time to connect, and I can get a better sense of what you're looking for, what your tech skills are, what you're doing, what you might be looking for, and see if we have any opportunities at Bloomberg that might fit. So Bloomberg, again, we're a tech company. We were founded in the early 80s right here in New York City. We have over 325,000 terminal subscribers. We have customers in 170 countries, and we have over 20,000 employees across the world, and 6,000 of those employees are software engineers. We have over 150 technologists in data science doing AI and machine learning work at Bloomberg. So what is Bloomberg? So at a very high level, We're a technology company and our software supports the finance industry. And the main product that we sell our clients is called the Bloomberg Terminal. It's really a software solution that has all different types of financial data as it relates to the financial markets, related to obviously finance data, news data, and analytics that our clients can use to make educated decisions around the market. We have engineers working all across the Bloomberg Terminal and working on all different types of communication platforms and analytics tools and trading systems and internal applications. So it really runs the gamut in terms of what we offer. But just to give you a sense of the scale of our system and the amount of data that we process over 120 billion pieces of data every single day. We ingest over 2 million news stories on a daily basis, coming from over 100,000 sources. And we have a couple of different proprietary communication platforms on the terminal. One of them is an email system and one of them is a chat system. And through those networks, we process over 1 billion messages every single day. So for someone who's really excited by large amounts of data, Bloomberg is a really awesome place to be. Again, here's the form that I will post again in the chat in case anyone missed it. But again, it's great to have you here. And now I'm going to introduce our speaker for tonight, Xiaoxiao Wang. Xiaoxiao, if you want to, you can share your screen now.
Okay. Can everyone see my shared screen? Hello?
Yes.
Can people hear me?
Yes, we can see and we can hear you.
Okay, cool. Good afternoon, ladies. My name is Xiaoxiao Wang. I am a software engineer working in Bloomberg. My talk today is building a scalable and highly available pub/sub application. This is the form you want to fill in if you are interested in opportunities in Bloomberg. This is the outline of my talk today. First of all, Katie and Cindy has already gone over some information about Bloomberg, about Women Who Code. So I will give a brief introduction of the function that our team maintains. And in the motivation part, I will highlight the challenges we have to deal with. And given those challenges as background, I will talk about system designs. And specifically, I will compare our old architecture with our new design and explain a few decisions we made along the way. And after that, I will summarize the talk and take questions in the end. This is about Bloomberg. So we are from PORT department in Bloomberg. Our system analyzes millions of financial assets and streams data to a large number of clients. Our clients can make their personal portfolios by adding all kinds of financial assets, such as stocks, bonds, options, so on and so forth. A simple example can be your 401k. Let's say you make some investment using your 401k. We should be able to evaluate the risk of your investment. We can calculate the profit and the loss and tell you the major contributor to your portfolio, so on and so forth. There are also indices, which are special kind of portfolios. I believe we have all heard of SPX 500, Dow Jones, and so on. Our team provide real-time analysis for clients' portfolios by collecting market data from various data sources. The challenges for us are twofold. First of all, the amount of messages and topics we have to deal with is huge. Think about it, we have to handle ticks of securities from almost every market in the world. And secondly, to guarantee the quality of our service, we have to make sure that data transfer is efficient and reliable. So this comes to the motivation of this project. As we said, we collect financial assets updates from various data sources whose load is often limited. And we have to efficiently and reliably deliver those data to a huge number of data consumers. Therefore, we have to build a pub/sub system with large throughput and high availability. So let's talk about system designs. I will give a brief introduction to the old architecture we maintained, and I will talk about our new design. We will discuss about the advantages of the new design and a few decisions we made along the way. So this picture shows our old architecture. In this architecture, each server is self-contained. Each of them directly subscribe to data sources independently. Let's explain the example here. Suppose a client has IBM in his portfolio, and this client lands on a server. So this server will subscribe IBM to data source and get stream data. Now let's say another client also has IBM in her portfolio, and she happens to land on a different server. Since each server is self-contained, this new server has no idea that the other server has already subscribed to IBM and already get streaming data. So this new server has to make a brand new subscription to the data source again. So we can see that in this design, there are lots of duplicate subscriptions to data sources. Therefore, the scalability of our system is limited by the capacity of various data sources, which means it is very difficult for us to spin up new servers and to serve more clients, because this could increase the load to data sources significantly. And apart from that, since subscriptions on different servers are maintained separately, we often see inconsistent data, and this is very difficult to debug. So this slide illustrates the ideal architecture we want to build. We think it would be nice if we can take out the data collection logic and make it as an additional layer between client and the data sources. That is the data producer shown here. We'd like the data producers to make unique subscriptions to data sources and publish data to those data consumers. This design eliminates duplicate subscriptions to data sources and takes control of scalability. So of course, nothing is free in the world. There are some challenges with the new design as well. First of all, subscription load must be well balanced across data producers. Otherwise, a producer with higher load could lag behind. And secondly, data producers need to be fault tolerant and highly available. Now that each of them are single source of a particular security, we have to make sure that if one of the data producer goes down, other producer in the system should be able to detect that and take over the load used to be served by the failed one. Only in this way, we can make sure that user experience will not be interrupted. And last but not least, we have to transfer large volume of real-time market data to hundreds of data consumer instances. So these are the solutions we came up with to tackle those challenges. We implemented a consistent hashing algorithm with multiple virtual nodes based on Apache Zookeeper to deal with load balancing and failure recovery. We also implemented efficient and on-demand communication between data producers and consumers by introducing a distributed caching layer for data storage and data retrieval. So let's first talk about load balancing and failure recovery. In our system, load is considered to be proportional to the number of financial assets. Their subscriptions must be evenly distributed to producers in a non-overlapping manner to have load balancing and to avoid duplicates. And the producers should allow nodes to dynamically join and leave while maintaining the load balance, all without interrupting the live data streams. I will explain the method we use to achieve this. I will first talk about the consistent hashing algorithm, and I will talk about Apache Zookeeper, which we used to coordinate producer ring states. So I will spend a few slides talking about consistent hashing algorithm. So we can consider the hash space as a ring starting from 0 to a big positive number. And we can map each data producer to a point on the ring by hashing them to some positive integers. And now a subscription comes. We have to decide which producer is going to serve this subscription. The method we use is to hash the subscription to the same hash space so that it will be mapped to a point on the hash ring as well. And then we go clockwise along the ring until falling into the first producer whose hash value is greater than that of the subscription. In this case, it is producer B, and the producer B is going to serve this subscription like this. So if you have more subscriptions, you just repeat whatever you did before. That is, you keep hashing the subscriptions and finding the data producers by always moving clockwise. So in this example I show here, there are 6 subscriptions. 2 of them are served by producer B, and 4 of them are served by producer A. Another way of interpreting this is each producer is only responsible for the ranges right before it on the hash ring. Any subscription coming at this range will be served by the same producer. So you may have already noticed an issue here. The subscription load is not evenly distributed, and this is more or less due to the relative position of A and B on the ring, and therefore the ranges belongs to them are of different length. So how can we deal with that? To solve this and achieve better load balancing, we introduce a concept called virtual node. Namely, we do not map a physical producer to one point. Rather, we maintain a one-to-many relationship between producers and hash points. One producer can map to several points on the ring, and we call them as virtual nodes, so that each physical producer is responsible for several smaller ranges on the ring. From this example, we can see that with a duplication factor of 2, one producer has 2 virtual nodes, and the load is distributed more evenly between the 2 producers A and B. Let's talk about failure recovery. Suppose you have 3 producers in your system. Each of them serves some number of subscriptions. And for whatever reason, producer A goes down, we have to transfer the load used to be served by A to the other 2 producers. Again, we repeat whatever we did before. These 3 subscriptions used to belong to producer A, and we take them, go clockwise on the ring. We will see that now they belong to producer C. And similarly for this subscription, it used to be served by A, but now we have to migrate it to producer B. So we end up with a setup like this. If we use traditional hashing to distribute the load, most likely we have to move all the subscriptions when there is changes in producers. But with consistent hashing, we do not have to move the whole world. From this example, we can see that if a producer goes down, we just need to migrate the load belongs to the failed one. So let's consider a different situation. Suppose now producer M comes up and wants to join the system. It can either be producer A recovers and come back, or because you want to scale up the system by introducing more producers. We have to assign some subscriptions to this new producer M. So how can we do that? First, we need to hash M and map it to virtual nodes on the ring. In this case, it is mapped to this point and this point on the ring. And then we can easily see that now this subscription belongs to producer M, and this subscription belongs to producer M. So we need to take them away from producer C and the producer B respectively and reassign them to the new producer M. So this would be the new system. From the above discussion, we can see that with consistent hashing, we can dynamically add or remove producers from the system without affecting live data streaming, this is definitely a feature we want in our design. So the next question for us is, how are we able to know the available producers and monitor their liveness? We adopted Apache Zookeeper to make it possible. Apache Zookeeper is a centralized service that provides high performance and consistent coordination for distributed applications. We have data consumers monitor the liveness of data producers via Apache Zookeeper. So this is how we use Apache Zookeeper. We have each data producer registers an ephemeral node under a root node inside Zookeeper server. And we have each data consumer registers a watcher to this root node. Any of the data producer change will trigger those watchers and notify all the data consumers. Those data consumers can then query Zookeeper server for producers that is alive. With this information, we are able to build consistent hashing rate. Okay, so I will talk about how we implement the algorithm. So first of all, load balancing. A local hash ring is maintained in every data consumers. They are implemented as an ordered map of available data producers acquired from Zookeeper. And each of the data consumer also maintains a map of subscribed financial assets. On data producer side, they keep count of how many data consumers are subscribed to an asset. And this diagram shows the load distribution of our system. We can see that it's not that bad. And it's worth noting that since the load on each of the data producer is much smaller compared to what we had on each of the server in the old architecture, a small variance is still acceptable. So for implementing failure recovery, we define a concept called a transition plan. A transition plan means you need to remove some of the assets from some of the data producers and reassign them to some other data producers. When there is a data producer change, each of the data consumer will calculate something called transition plan for migrating financial assets from one to the other. And by design, one transition plan can take care of multiple producers going up or down in one Zookeeper event. And the consumers will be executing the transition plans independently by sending out subscribe or unsubscribe requests to producers. So from this design, we can see that there is no leader that dictates the transition when there is producer change. The reason is because naturally, each of the data producers should be able to know the financial assets that it needs data from. So each of them is responsible for the failure recovery of itself on the data producer side. By doing this, there is almost no bottleneck in the failure recovery of our system. And we also find that the recovery of single instance takes less than a second. Then I will talk about some implementation challenges we have to deal with along the way. So first of all, as I mentioned, we use an ordered map, and we use hash values, which are unsigned integers as the key of the map. And because we have millions of financial assets in our system, it is very difficult to choose a perfect hashing function that can avoid hash collision completely, which means we have to deal with hash collisions ourselves. And then we found that it is better to chunk big requests into smaller ones. And the reason are twofold. First, there's size limit of the request we can send out using Bloomberg architecture. And secondly, we find that by sending smaller requests using thread pool, we can make use of the multiple thread in data producer and data consumer, and so that the transition plans can be executed as quick as possible. And then the transition plans should be executed sequentially in a single separate thread. They have to be executed in a separate thread other than the Zookeeper thread, because we want to keep the Zookeeper thread always available and always listen to Zookeeper event. And they have to be executed sequentially because we want to respect the count we maintain inside data producer. We do not want to unsubscribe a security before we subscribe it, because in that case, the ref count will be messed up. And last but not least, if a data producer goes down and then come up, we will treat it as a completely different data producer. The reason is because it has no memory of the subscriptions of the assets it used to have before it dies. And we differentiate this by adding timestamps to them. Those timestamps will be attached to subscribe and unsubscribe requests sending out from the data consumers, so that we can make sure that a data producer will not process requests belongs to its predecessor. So data transmission is another challenge for us. To transmit data from producers to consumers, we have investigated many internal or open source technologies. We have those requirements for the data transmission method. First, it needs to have high throughput to support a large amount of data. Some of the technologies have to ship all the data to every machine in the system for the subscribers to filter and to choose from. This will result in a huge network load, which is impossible in our case. And secondly, it needs to have fine granularity to support arbitrary financial asset prediction schemes. In other words, it has to support millions of topics corresponding to millions of financial assets, which means Apache Kafka may not be a good choice for us, because in Kafka, the typical number of topics are just a few thousand, despite that it claims its recent versions can support hundreds of thousands of topics. It's still not good enough for us. So this is our choice. We choose to use a distributed Redis cache to share data from data producers to data consumers. Redis is a distributed in-memory data structure store with high performance. So in our system, our data is sharded into multiple instances of Redis caches. Each of them is running only at 30% of their capacity. And the consumers will pull the data on demand at certain frequency based on their SLA. So one thing worth mentioning is that a lot of the financial assets do not tick all the time. Many of them only ticks a few times a day. To reduce the load of cache pooling, we introduce a concept called quick read and full read. This means we will attach a lightweight version field to different part of the data. Quick read will only read the versions, and only if it detects a version change in quick read, we will do a full read of the whole data. These two diagrams shows the relative amount of quick read we performed. The left side of the of the diagram is the number of times we do quick read and full read, and the right side is the amount of bytes we pull in when we do quick read and full read. The blue curves corresponding to the quick read we processed, and the green curve correspond to the full read we processed. And we can see that the difference is obvious in these two pictures. So to summarize, with Redis, we can scale up the system easily. Our data can be partitioned into as many Redis instances and machines as necessary, enabling us to support larger data size and a higher request volume in the future. We keep each of the Redis instance running at low utilization because we want to be able to accommodate market volatility, and we want to eliminate the possibility of data eviction. Okay, this is the summary of the talk. So by moving to a distributed architecture for data collection, we are able to eliminate duplicate subscriptions and take control of scalability. By making use of consistent hashing algorithm, we can achieve load balancing and dynamic failure recovery. And with the help of Zookeeper, we do not need persistent storage for failure recovery, and we don't need to do leader election for recovery either. And then by implementing quick read and full read, we should be able to do scalable data retrieval. And finally, by separating subscription and business logics, our system has a cleaner architecture and is easier to maintain. So this is some reference of the talk. Thank you. And I will be happy to take questions. Okay.
Feel free to unmute yourself and yeah, ask any questions. I have a question. What did you, because I've never heard of hashing rings before, right? Mm-hmm. And yeah, it's all actually kind of interesting, the choice to go like for a distributed Redis cache over Zookeeper as well. What did you find was, I think, like the most complicated part of this whole, or challenging part of this whole, building out this whole new architecture?
I think the most complicated part would be implementing the transition plan, because consistent hashing is a very common algorithm. You can see it in a lot of the references and the online documents, but it's very difficult to find a good implementation that fits our need, and we want to tailor the concept and translate it into code and do the real implementation. Because it's a distributed system, there's millions of assets. You send out a lot of subscribe and unsubscribe requests. It's very difficult to test and debug. So yeah, that's it.
I have a question.
Sure.
How long did this type of like architecture change happen? Like, was it like a 6-month project or years in the making? And then I guess the second part of that is like, how do you go into like planning some of these decisions? Like, do you do like proof of concepts for them?
Sure. I can answer the questions one by one. So first, how long does it take us to make such transition? We've been working on this for almost a year, and yeah, it takes longer than what we expected, because as we moving things, we keep discovering new stuff or corner cases or bugs we have to fix, so on and so forth. And the second question is, do we do proof of concept? we do not build a proof of concept of the whole system, but before we make the choices, we benchmark things. For example, when we decide to use Redis, we benchmark Redis performance, and we also collect stats from the system we are maintaining, like how much data we have to transfer, we have to deal with, and what is the frequency of the updates. Can Redis be able to handle it, and how many Redis instances we need to use. We benchmark Redis performance in another way. And
Nice.
of course,
Sorry.
so for Zookeeper, it's not that difficult to build a proof of concept. You can write some testing code to verify if the changes can be reflected. Yeah, if that answers your question.
Yeah, thanks so much.
Hi, my name is Shweta, and thank you for the talk. You alluded to testing, and that was my question. Is one of my challenges with a pub sub setup is how do you successfully accomplish end-to-end testing? How do you account for latencies and still ensure that your tests are valid and are mimicking the real production environment? Did you run into that challenge, and how did you work around it?
Okay, I think that's a good question. As I said, we had an old architecture where the servers will subscribe to data sources directly. In the transition period, we maintain a double ticking method, which means we will keep the old architecture, which is subscribing to data source directly, and we will also pull the data from the cache. And in the background, we will make a comparison between the data we get from the two data sources. And we will observe if there is any difference, if there is any lag of data. And I think so far, so good.
Oh, that makes sense. Thank you.
Okay, thank you.
Hi, it's Kathy. I was just wondering, I had one question. Maybe you already covered this, I'm not sure. So in the big circle, remember the big circle with the caching?
Yes.
I didn't understand if one, I don't know what they were, subscribers dropped off, why everything wouldn't just land in the one afterwards and overload it.
Why wouldn't everything what?
Because they're kind of like hashed all around the circle. So it's not like a whole segment of the circle that would, like if one dropped out, I'm trying to understand why all of, maybe go back to the circle if you could.
Okay. Failure recovery?
Yeah. So you have C. Why does everything in C not land in B, which is BV1, which is right after it? Like if C drops off, oh, A dropped off in this case. I guess A dropped off. How did, I don't understand how it ended up not all routing to the one right afterwards. Like I would have pictured if A dropped off that everything would land in C if it was the one right afterwards.
Oh, because this subscription used to be served by A. Now we have to migrate it, right? So we take this subscription and go clockwise along the ring. The first data producer we met on our way is producer B. So producer B will take care of this guy.
So there was like a migration around. Okay, I missed that part. Okay,
Yes.
cool. Thank you.
So I also have a question about this failure recovery part. So in this graph, like when you say the data producer A is, let's say, is not reachable, and you have to move all the subscriptions that has been managed by A to C. Like, where do you keep the history of what has been managed by data producer A? How do you know what will be migrated into into C? Where do you keep track of that?
Okay, good question. I think I covered this a little bit, but maybe I didn't explain well. Data consumer knows all of the subscriptions it needs data from. And when data producer A goes down, consumers will be notified, and they will act according to such change. So on consumer side, it knows the status of the ring, and it knows the subscription used to be served by A, and then it gets notified that A goes down, and the consumer will make the adjustment, will make the transition according to the change, and they will send subscribe or unsubscribe requests to B and C in the system. Does that
Okay, I see. So it's actually initiated by the consumer, not
by the consumer.
Oh, okay. Thank you.
Sure.
Hi, I might have missed this on the title slide, but I was just, my name is Jenny. Hi, thank you for talking.
Hi, Jenny.
I was just wondering, are there any cases when you would want to use this PubSub subscription service versus when you wouldn't want to use it? Like, what are the, like, I guess I'm wondering, when would you want to consider adding this architecture versus maybe going with a different approach?
I think if there is something ready for us to use, like say if Kafka can support that many topics, we would rather use Kafka. We have investigated those kind of technologies, and we don't find a good fit for us. That's why we decided to build this whole architecture. And I'm not sure if it's a good choice for others if they do not have that many topics or if they do not have that much data. I guess we made the decision by collecting numbers from our system and benchmark or look into documents of the technologies on shelf.
I guess I'm wondering more of a PubSub architecture in general. Like if I have an application and I'm thinking of introducing Kafka or any kind of PubSub type of architecture, when should I consider using it versus not using it, or should I use it all the time? What are your opinions?
My opinion would be collect data for the system you want to build and see if Kafka is able to satisfy your requirement, is able to satisfy your need. If it's not, then you might need to either implement something yourself as what we did, or I don't know. Thank you.
Are you, actually, if you don't mind, did you mean like PubSub versus some other sort of like streaming architecture or something that polls differently, or I guess, is that what you meant by your question?
So for my question, so we use Kafka in some of our application services, and sometimes what I've noticed is in situations where we decide to use Kafka versus not Kafka, you might think of like maybe we decide we need to send an email out to customers. That's not something that needs to happen immediately. So it can be an asynchronous request. So they do that using Kafka queues, right? With a PubSub system where you're publishing a topic and reading the topic. And it's very popular in like highly distributed systems. But sometimes they decide that, no, we need to make a direct call to another service and wait for a response. So, so my question was sort of a general architecture question. You know, when do you decide you need like an asynchronous system, like like a publish and subscribe application system versus when you need something that responds directly. Answered my own question a little bit, but I'm wondering if there's more use cases than just whether or not a request can be asynchronous.
I guess what we've followed in Shutterstock is if the requester or the person dispatching the request or handling the request, person as in the application handling the request, needs to process the response before performing the next operation, then it is not a good candidate for PubSub. Versus if the entity that is handling the request does not need the response back to perform subsequent operations, then we use PubSub. That's very high level general rule of thumb, but it's worked in most of our use cases.
Thank you.
Great. So I guess if there's no more questions, that's the end of our talk. Thank you, everyone, for coming in. And as a reminder, if you are interested in opportunities at Bloomberg, please follow the link in the chat and or copy paste this directly and fill out your information.
Thanks for coming, everyone.
Thank you.
Thanks for presenting.
Thank you.
Thank you. Thank you.